All right. Good morning, everyone. Yeah, I hopefully everyone felt pretty good about the exam yesterday. I know that the last thing you want to do on a day that we don't have school is to watch the lesson, but we do have to continue on and try to get done with chapter 7 here and start into chapter 8 and continue working through chapter 8 as well. Okay. So what I'd like to do today is, yeah, we're going to finish up with the chapter 7 material. We're going to finish talking about metals, and then we'll start talking about chapter 8, which will deal with covalent bonding. And I think studying metals is a good way for us to kind of segue into that discussion of covalent bonding, because there are certain shared characteristics between the metallic bond here, which is the interaction between metal atoms, and the covalent bond, which is the interaction between individual two separate atoms and how they form the interaction between those two separate atoms. Okay? All right, so let's go ahead then and let me go ahead and share my screen here with you. And let's pick up where we left off with on Monday let me go do this here, with the discussion of metallic bonding. Okay. Now, this idea of bonding in metals seems a little bit odd, I think, to folks who are kind of new to this, which that means you folks there. Okay. And this idea of bonding in metals doesn't seem to be quite clear. The issue then that we have then is, how do we know that there are bonding? Now, remember this idea of a bond, and I want to talk about this really quickly to make sure everyone's clear on this. When we talk about this term bond, it just means the interaction. It's what ties together atoms. So a bond is simply an interaction. It's an interaction between atoms. Okay. And so what we need to make sure we understand is that what we've talked about so far is we've talked about the ionic bond. Okay. And so there's three types of bonds that we want to refer to, that I will be referring to. I will be referring to the ionic bond, okay, which is what we learned here in chapter 7. Okay. We will be talking about the covalent bond, okay, which is the what we will cover in chapter 8. And then the third type of bond is the metallic bond. Okay? And this is also covered in chapter 7. Okay? So three types of interactions between atoms, and that's how we will define a bond. A bond is going to be defined then as an interaction between atoms, and there's three ways that atoms will interact with each other. Okay? There are three ways that we know of that atoms interact with each other. Now, remember, with the ionic bond, we know of its existence. We know that the ionic bond exists from observations that we can make about the macroscopic properties of ionic compounds. Ionic compounds have a very high melting point. We talked about that. You saw that on the exam yesterday. Okay, ionic bonds, then ionic compounds are solids at room temperature. They are crystalline in nature, and that they conduct electricity when they're melted or when they are dissolved in water. So with that said, then I want to refer you to this idea then that the bond holds atoms together. And if a bond holds atoms together, it's going to take energy to break it apart. And that's why with ionic bonds, when we talked about this in ionic compounds, they have such a high melting point because it takes a lot of energy to break that interaction. And so what we need to make sure we keep in mind then is that when we talk about bonding, okay, we were talking about the interactions between atoms. Okay, so make sure you keep that in mind. And so the interactions that keep these atoms together will result then in certain properties. One of the main properties that we can look at is the physical state of atoms of a substance when it's at, let's say, room temperature. So we know then that atoms, if elements can form a solid, okay, the solid state, that means then there must be a very strong interaction or there has to be interaction between the atoms to hold it together. So we learned about this back in chapter back in chapter uh, 2. Okay, we talked about this back in chapter 2, that in the solid state, and let me just go ahead and refer this to you. Okay, so in the solid state, The solid state of matter, remember there's three states of matter. The solid state of matter is the one in which the atoms then are, if we take a look at it, okay, packed very closely together on the atomic level, on the very microscopic level, okay, and that there are interactions that hold those atoms together in the solid state. We didn't define it as such back then, but we have it now. What are those interactions? The bonds. Okay, so remember the solid state then have these interactions that hold those atoms in place. Okay, and those interactions have to be pretty strong. Those interactions have to be fairly strong. So in the for ionic compounds, the interaction there are the ionic bonds, the attraction between positive and negative atoms. Okay? And so that's a very strong interaction. Here, what we can see then is, let's work backwards a little bit. Here are examples of some metals here. Okay? And so these metals are in the solid state. These metals are in the solid state, which means then, folks, that there has to be an interaction that holds these atoms together. So let's take a look at gold here, for example. Okay? So you can imagine gold then being a series of atoms, okay, being held together, okay, in place here. So there are, let's just take a look at a 3 rows of these metal atoms. So if we said then that substances in the solid state have very strong interactions here that holds those atoms together, okay, here we have a sample of gold, okay, that is in the solid state. So therefore, these atoms of gold must have some type of interaction, therefore some bond that holds them together. Now, gold atoms, understand, are neutral. We already know this, and let's make sure we understand this. And let me get this for you. We know then that with the gold atom, and I don't remember this off the top of my head, that a single gold atom, and let's go ahead and let me draw it over here. So a gold atom, okay, let's go ahead and write down the composition of gold atom. The gold atom then has 79 protons, okay, 79 new electrons, and a certain number of neutrons, and we won't refer to that right now because that really doesn't, that helps identify the isotope for us, but not necessarily the bonding. The bonding occurs here with the electrons. Now we know then that this gold is a neutral atom. Okay, the elemental gold is a neutral atom. Yes, can gold become an ion? Yes, we saw it. It could become an ion. It can lose an electron in its 5s orbital. I'm sorry, in its 6s orbital to become then the gold ion. So we saw that happen. But this is elemental gold. From what we have here, this piece of gold right here, this is elemental gold, which means that it has 79 protons and 79 electrons. It is not an ion. So it can't be the ionic compound, that ionic bond that holds two gold atoms together. Okay, so let's imagine that we have two gold atoms sitting right next to each other, both of them having 79 protons and 79 electrons. Okay, so how then can we explain this interaction? If it's not ionic bonding, okay, it can either only be covalent bond or metallic bonding. Those are the only three types of bonds that we know of. Okay, and so if it's not ionic bonding, and covalent bonding, we won't start talking about till chapter 8. What is this metallic bonding that I'm referring to here? Okay, okay. So with that said, then the way that you can imagine the interaction, that is the bonding between metal atoms, is that we have then a series of cations. Okay? We have a bunch of, so let's imagine this, that we have a series of cations. And why do we refer to these as cations? Because what we're talking about here then is we're talking about the protons. So let's imagine then that we have 79 protons here. Okay, let me go ahead and draw this. Let's go ahead and let's draw that interaction down here. Okay. All right, so let's imagine then that we have a gold atom here and a second gold atom there. Okay. So each atom then is comprised of a nucleus that has 79 protons. That means then we have a positively charged core right there. So that is how you can consider this cation makeup. And I'll show you this in just a moment. Okay. So you have then two protons here. Okay, two protons, two nuclei here, both with a charge of a positive charge. These have 79 protons. Now, what we're going to do then is, for right now, we're not going to consider the core electrons. So we're just going to take a look at the valence electron for gold. Okay, so gold, each gold atom, remember, has a valence electron, one valence electron in the orbital. Let's make sure we keep that in mind. So we have a 6s1 electron, 6s1. So that means that around each one of these proton nuclei then is a, and I'm just going to draw this, and I'm only going to draw the outermost 6s orbital. Okay? So there's the 6s orbital right there. Okay? So we have the 6s orbital right here for both of these. So there are the 6s orbitals, and again, we're ignoring the valence electron, the core electrons underneath, and we're only going to examine then the valence electron. Let's go ahead then. Let's take a look at that one valence electron right out here. So there's the one valence electron from the first gold. That's the second valence electron from the second gold. Okay, so these valence electrons here, they are orbiting around the nucleus. Okay, they're orbiting around the nucleus. The theory, the idea then about the theory that lies behind the metallic bond, the way that we explain the metallic bonding is in a very simple way. What happens then is that we refer to these electrons, and as they move around this nucleus, they can shift over and move around that nucleus. Same thing with this this electron here. That as it moves around its nuclei, it can shift over and start moving around this other gold atom. Okay, we refer to this as delocalized. Sorry, I gotta spell that right. It's called delocalized electrons. Okay. These are delocalized electrons, meaning then that they are not located in a single location. They are free to move around from one gold nuclei to the other. Okay. They are not localized. And this coincides with what actually we learned about. This coincides with what we learned about electrons back in chapter 5 when we talked about the uncertainty principle. Remember we talked about the uncertainty principle back in chapter 5 principle? And we learned then that back then, what the uncertainty principle tells us is that we can't be absolutely sure where an electron is located. We can say generally in terms of where it's located. We can talk about its energetics, okay, but we can't be certain about its actual location because they're too small and they move at a rate that is close to the speed of light. And so this delocalized electron, this idea of delocalized electrons for metallic bonding actually fits in very well with the uncertainty principle that Heisenberg proposed. Okay? And so that's what we have right there. And that essentially is the metallic bond. The central core idea behind a metallic bond is that you have electrons that are delocalized. And that's why we were saying then that you have these this idea that they're cations packed closely together. Why? Because it's the nuclei that are packed closely together. However, they are kept apart from one another. They don't repel one another for one very simple reason. You have these electrons that are flowing around. Now here, I've only illustrated for you 2 electrons. You can imagine then that in a very small sample of gold or any sample of metal for that matter, okay, there will be billions upon billions of electrons, atoms, all packed closely together. Okay, and so what we do then is we say then that here's the example again of, I'm sorry, we're going to do this. Here is our metallic bond. So here now I've drawn more of our gold atoms. Let's imagine that these are all our gold atoms, or the nuclei that we've talked about, the core electrons that we talked about. So these then are the nuclei, okay, the individual nuclei for each metal atom. Okay. All right. And so if you notice that you have all these nuclei packed very, very closely together. And this is just a two-dimensional representation of the metal itself. Okay. All right. And so here you have then the valence electron, the individual valence electron for each nucleus. Okay. So there it is. So if you followed my example just now, valence electron. Okay. And what these do then is, if it's not, and so these valence electrons then aren't just being shared between two nuclei, they're being shared between all of the nuclei collectively. That means that they are free to move around this whole region of space here. They can move from one nuclei to another because what they are is, remember, they are delocalized. The other way that I try to kind of imagine, try to get you to imagine this is that these electrons then are shared. They're shared between all of the atoms, so all the nuclei. So that's why then, if this is true, then actually each nuclei, they don't repel it. They don't repel each other, even though they're packed really closely together. They don't repel each other because you still have these electrons moving between them to keep them separated from one another. Okay, so if you can imagine that you have this layer of electrons moving around every single nuclei, keeping them separated. And so the way that we describe this model for metallic bonding is that we refer to it as a sea of electrons, because these electrons are free to move around all the nuclei. Okay? And so the metallic bond then is, and the key to understand is that we have, instead of free floating, these electrons are free floating. And again, the term free floating, valence electrons, I don't particularly like that, but I think it's a term that most people can identify with. The better, the more accurate term then, and this is what I want to make sure that I make clear to you. This idea of free floating electrons is described then as delocalized. This is a set of delocalized electrons, and that's probably the better way to describe it. Okay? And this concept of delocalization is going to be really important. This is why I was telling you that with metallic bonding, when we discuss metallic bonding, it allows us to segue very smoothly into covalent bonding. It's because with covalent bonding, we have delocalization of electrons as well. This time, the delocalization occurs only between two atoms, two nuclei, rather than a whole bunch of nuclei, instead of a whole bunch of it. So you have these electrons that are in motion, but unlike the motion here, where the electrons are free to move across a large plane of nuclei, they are with covalent bonds. They are restricted only between the space between. They're restricted only to the space between two nuclei. Okay, and so with that said, we will get to the discussion of covalent bonding in a little bit. Okay, but that's what metallic bonding is. And we describe then metallic bonding as a sea of electrons. Okay? All right, so that's the theory. That's the explanation that we give. That is the atomic level explanation. That is the microscopic explanation that we give. But that explanation doesn't hold water. It doesn't work unless there is evidence that we can observe to support it. Okay? So is there evidence of at the macroscopic level that we can observe to possibly support this idea of sea of electrons, or this idea of delocalized electron? And there should be. Just like with ionic bonding, we saw evidence of, we were able to obtain evidence to show then that the ionic bonds do exist. The fact that they have a positive, the fact that they conduct electrical charge shows then that those atoms, those ions do exist. You have charged ions. The fact that they interact with one another gives us the solid state. So we have them, and we can observe then certain properties on a macroscopic level that can support this idea of ionic bonding. We have to be able to obtain similar observations on a macroscopic level to support this idea of metallic bonding, or the sea of electrons. Okay? So let's go ahead then and let's take a look at what we have. Okay? Well, let's review what we know about metals. Okay, let's review what we know about metals. We talked about this back in chapter 6. We know then that metals are good conductors of electricity and heat. We know then that metals are ductile. That means they can be shaped. They are malleable, which means that they can be shaped into different shapes. That they're ductile, which means that they can be stretched out into very, very thin wires. They're good at reflecting light, and they're solids at room temperature. And we know then that those are some of the characteristics that all metals form. If the sea of electron model here cannot explain why metals behave in the way that we just described, then it's not a very good model. Okay? Models that we are always, models need to have support from observations. We have to be able to observe, and there has to be data. There has to be the observations must support the model, or else the model doesn't. If it doesn't fit the observation, it's a bad model. Okay, so let's go ahead and let's take a look at then how then the sea of electron model here does help to explain properties of metals. Okay, let's take a look at these here. Okay, so let's take a look first then at the ability of metals to conduct electricity. Okay, so let's go ahead and let's take a look at the first one at the very top right there. Okay, so here on the left, I have a depiction in slide in frame A. Okay, so here I have depicted for you the metal C electron, the metallic bonding. Okay, so here it is. We have the I'm sorry. Okay, so here is the metallic bonding. Okay, so that is the picture of the metallic bonding. C of electrons, delocalized electrons. Okay, so here it is. We have the electrons moving from one nuclei to another. Okay, all right. So with that said, for frame B here, then it helps us to see then how metals are good conductors of electricity. Okay, all right. So first of all, we have to, in order to discuss the metals being a good conductor of electricity, we got to backtrack. I have to backtrack just a little bit, okay? Not too much, okay? Because we don't want to spend too much time in physics here. But we have to explain what an electrical current is. Okay? The simplest way that we can describe an electrical current, it's the movement of electrons from high potential to low potential. Okay, so it's the simplest way that we can define electrical current. Okay. All right, so what does that mean here? The potential definition here. If you want to imagine this, think of the movement of water, which also can be described as a current. So if you take a look at the current in a river, the current in the river occurs because you have water moving from one location to another. The movement of water can be described as a current. Okay? So here, it's a similar way that we can describe current. It's the movement, and instead of a movement of water with electrical current, we are describing the movement of electrons. But why does water move? If you place water on a very flat surface, there's no motion. Think of a lake. In the lake, there is no current in the lake because the water pretty much is at the same elevation, at the same potential height. Okay, so that's what we refer to as the same potential. You lift that lake up on one end, so that one end is higher than another end. Then what's going to happen is that that lake full of water is going to start to move. It's going to start to flow, and you're going to get a current. So we say then that the higher end of the lake is at a higher potential than the lower end. Okay, so higher elevation, high potential, lower elevation, low potential. And when you set up a potential difference in that manner, then you get water to flow. Okay, so a difference in potential, this means then that you have one place that's higher up than one place that's lower. That's how you want to kind of imagine this. Okay? So what is the high potential for electrical current then? An area where you have a lot of electrons, okay, that's the high potential, okay, and the area where you have very little electrons, and that's the low potential. And so electrons want to flow from an area where there's a lot of them down to an area where there's not that much of them. Okay, so if you take a look at this picture here, then we have then on the left-hand side here, we have high potential. Okay, so we have an area of high potential here. That means you have a lot of electrons. Look at all the negative charges here. Okay, and on the right-hand side, you have low potential. Okay? That means you don't have that many electrons on the right-hand side. So that what does that mean then? These electrons on the left-hand side, they want to go ahead and they want to move. They want to move and they want to move in that direction. They're going to move in that direction and they're going to try to make it to the other side. And that's what they want to do. Okay. Now, with that said, that's electrical current. How is it then that metals that are good conductors of electricity? What could that? How can we explain that? Well, let's use our metallic bonding here example to help us out. Okay, so here, let's imagine then here is our electron on one side. There's our electron. I'm going to color it in red so you can kind of see it. Okay, so we have our electron on the right-hand side here. Okay, and it wants to get to the other side. Okay, so let's go ahead and let's draw that in there. Okay, so there it is. There is our electron, and it wants to make it to the other side. Okay. All right, so when it gets pushed into the metal, okay, so let's go ahead and let's do this. It moves into the metal. Okay, so there it's going to move into the metal. What it's going to encounter then is a bunch of other electrons. Okay, a bunch of other electrons. what it can do with the other electrons. And remember, the current then is just the movement of electrons. It doesn't necessarily have to be this specific electron that moves over. Okay, so what you can imagine happens that it goes in and it collides. And let me go ahead and let me redraw this one here. It collides, since it's moving into a sea full of a bunch of electrons. It collides with that electron. Two negative charges are the same. They repel each other. So that the incoming electron, that red electron that comes in, it's going to collide with this electron that is already in there. Okay. What this electron then does is it gets bounced. It gets bounced, and let's say then it bounces. Oops, sorry, and it goes now, and it bounces off, and because it was hit by this red electron, it's going to go and it's going to change its course, and it's going to bounce, and it's going to hit that electron right there. And so as a chain reaction, this electron now gets kicked out on the other side. Okay. And so what happens is on the other side, yes, we don't have the exact same electron that's moving through, but we do have an electron that does move through. Okay. It's a different electron, but it is an electron that does move through, and there it is. The current flows very easily. Okay. So that's the idea of why metals are good conductors of electrons. Why the sea of electrons then helps to quickly conduct or to move an electron through. And again, it is not necessarily this electron that actually makes it all the way through, though you can argue that as well. Okay, but the idea here then is that since you have a sea of electrons that's moving around, okay, all moving around, this electron enters the metal, collides and interacts with an electron that's already there, and then you get a chain reaction in which you have one collision occurring after another to send out another electron. So different electron goes in, but we still have a net movement of electrons. So that is the reason why then, that's how we can explain then that that metals are good conductors of electricity. Okay. All right. So we also said then that metals are good conductors of heat. Okay. So conductors of heat. So in frame B here, we are going to take a look at then how metals are good conductors of heat. So let's go ahead and let's talk about how that works. Okay, conductors of heat. Okay, so let's go ahead then, and in the same way, let's quickly backtrack just a little bit, and let's talk about what heat is. Okay, so if we can define the electrical current as moving electrons, okay, heat then we can describe then, and let's let me go ahead and do this here. When we describe heat, okay, it's just the energy associated with motion. And we talk about this much more in hopefully when we get to the thermodynamics chapter. Okay? But it's the energy of motion. The heat is motion, and that's how you want to think about it. Okay, whenever you have something moving, it has heat energy. It will be associated with heat energy as well. And that's why we learned. Remember when, I don't know if you remember this, but back in chapter 3 when we talked about temperature, we talked about the Kelvin scale. We said then that 0 Kelvin, which represents the temperature at which there is no more heat. What did we say? When there is no more heat, I also told you then that all motion ceases as well. So there's a direct connection between heat and motion. Heat and motion. And so let's go ahead then and let's take a look at how the sea of electrons allows us to explain why metals are such good conductors of heat. Okay, so let's go ahead then and let me go ahead and do this here. So this is the first one here is going to be. So let me go ahead and write this in here so you can have this reference. So this is referring to conducting electricity. Okay, let's go ahead then. Let's take a look at why metals are good conductors, good at conducting heat. Okay. Okay. Let's imagine then we have a wave of heat right here. So heat is energy, and we're going to say that it's a wave of heat. Okay, there it is. Okay. And so remember, this is heat energy right here, which is energy associated with motion. Okay. We're going to heat up this left-hand side of the metal right here. Now, with the sea of electrons, folks, what did we say was true about all those electrons and what they do? the electrons are always in constant motion. They are always moving, which means then if you hit it with energy that is associated with motion, heat energy, you can imagine that what happens to these electrons here, that they start to move, but not only that, they start to move faster. You can imagine then that these electrons on this side here, they start to move around and they start to move faster. Okay, they start to change their trajectory and they start to move faster. And then what do? They're going to collide and they're going to hit this electron here, and it's going to cause this electron to start to move faster. So you get this chain reaction here of motion where one electron is speeding up, it hits another electron, causing that electron to speed up. And you see that happening in waves. And so it starts to spread from one side of the metal to the other, so that by the time then you get to the other side here, okay, and this final electron here is moving, it's going to transfer that heat to this side. Okay. So heat is going to be easily transferred through the metal because the electrons are already in motion and they're moving at a very high clip. Okay, they're already moving at a high clip, so they can transfer that energy very, very quickly. So that is why we see then that that metals then are good conductors of electricity, and why the C electron model helps to also explain why metals are good conductors of heat. C of electrons, electrons are in motion. You're adding in energy associated with motion. You're just going to go ahead and speed up that motion. Okay. All right. Very good. So with that said, then let's take a look at the last one. Okay. And that is metals then are malleable. Okay. And they are ductile, which means then that they can be shaped. The idea behind this is that when you shape a metal, and let's think about this, if you've ever seen a blacksmith work, or if you ever seen anyone work with metal, you really got to pound the metal to shape the metal. You got to really pull the metal, stretch it out in order to use a lot of force to stretch it out. Okay, and so what we're talking about here then is the application of force. Okay, so that's what we have here. Okay, so this large red arrow then is a force, and remember we learned about force. Okay, we apply a force, and a force then is described then as a push or a pull. That means then we're applying a large pushing motion onto the metal, or we're pulling that metal apart. Okay, so that's what we're doing here when we talk about applying a force. Okay, and so what I'd like to do is I just want to go ahead and share with you. Let's go ahead and let me save this for you. You can have this. Okay. Okay. I want to go ahead then and let's take a look at then, and let's take a look at this a little bit more closely. This idea of application of a force to whoops, let me go to the drawing here. Okay. Application of force to metal. Okay. All right. So let's imagine what we have here. Okay, so we're going to, so here are silver ions. Okay, silver ions, and we have the valence electron, C electrons there. So with each silver ion, remember each electron here. Let me go ahead and draw this in. Each electron is basically insulating, separating the positive charges from one another. They don't repel one another. Okay. All right. So here it is. We're going to apply force. We're going to push down on the metal with this pick here. Okay. So we take this little metal. Okay. So we take a pick here. Oh, I'm sorry, pike. Mr. N can spell. He knows a little bit of English. Okay. So we take this pick here and we push down right there. So you can imagine this on a microscope. That's what's happening on the macroscopic level. On a microscopic level, then we're taking our force right here. So there's the force, and we're pushing down on it. Now, when we push down on it, all the cations, so all the nuclei, they move and they shift. But because we have the C electrons here, the electrons move with them, keeping them again separated from one another. Okay, so therefore they don't break. Now, imagine if those electrons didn't move along with them, and we're going to see this in just a moment with the ionic bond. If the electrons didn't move with them, then what we would have then is we'd have a situation in which we have cations right next to each other, and then they would repel. And on a macroscopic level, what we would observe when that happens, that we would see a breaking occur. Now, is there a point? Can you keep on doing this? Keep on applying a force, a greater and greater force, and still the metals won't break? Obviously, no. We know that. We know then that if we keep stretching out a metal, at some point it's going to break. Okay? And so, yes, there is a limit to that, because you can get the You can apply enough force where you can pull, for example, on a piece of metal, copper wire, for example, and you can do this. Okay? You can pull out a piece of wire. The wire gets thinner and thinner. At some point, then the atoms do get close enough to one another. The nuclei do get close enough to one another to repel. And what do we notice? The wire breaks. Okay. So yes, there is a limit to this, but up until that limit, the metal does not break because of this very fact here, and that is the electrons, they move along with the nuclei. Okay, so we see that here. So the electrons move along with the nuclei, and they keep the nuclei separated from one another, and that happens within limit. Okay, within a limit, that does happen, and we can see that happening, and we can observe that on a macroscopic level. Okay? Now let's go ahead and let's compare them. Okay, to what we see here. I'm sorry. With the ionic compounds. Okay? Now we know that the ionic compounds are not malleable. They are not, and I'm sorry, I'm running low on time. Okay, so they're not malleable. They are very brittle. So for example, if you a piece of salt, a large piece of salt here, if I apply a force from the hammer to that piece of salt, that salt's going to break into smaller pieces. Okay, let's take a look at why that does happen. Okay, so we go ahead then and we apply a force here. We apply the hammer, and so here's our ionic compound held together by an ionic bond, positive and negative atoms. Okay, so you apply a force, and let's imagine you apply the force right here on this second column of ions right here. Okay, so what happens then is when you do that, you shift that column downward. You shift it downward, and take a look at what happens here, guys. If you shift it downwards, okay, and we're looking at this at a microscopic level on a single atom level. Okay, so if you shift it down, let's take a look at what happens here. We see then at this point here, okay, you have two positives, two negatives, two positives right next to each other. What you've done then is you have forced atoms then that are charged exactly the same. Okay, and what do like charges do? They repel. So as you exert this external force here to just shift this two rows down one single atom, you have then you force then atoms that are similarly charged right next to each other, and like charges repel. And what happens when we see this on a macroscopic level? Then they repel one another, and the crystal cracks. It breaks, and that's why ionic compounds are brittle. Okay? They are fairly strong in that sometimes it takes a lot of force, but sometimes it doesn't. But it does take a lot of energy to break that bond. Okay, but here we're applying a force. Okay, so with that said, then that's the key difference behind ionic bonding and metallic bonding. Okay? And we have evidence to support both of those. Support our observations for both of those. Okay? All right. All right, so with that said, then that's the metallic bond. That's what I wanted you to make sure that you are clear about. I just want to finish up by letting you know then that we have what are called alloys. Alloys simply that are mixtures of metals in the solid state. Okay, and so that's essentially what we have. The interaction between the different atoms are exactly the same. Okay, so we talked about mixtures back in chapter 2, mixtures back chapter 2. And so please make sure you review that. But then what we have then is with alloys, when you see the term alloy, it's just simply a mixture of metals. Okay? All right, very good, folks. We will start chapter 8 on Monday then. And so I'm going to go ahead and I will adjust the due date for the homework, the last homework set for chapter 7. I'll adjust that to be due on Monday. Please take a look at that. And then on Monday, then we will start chapter 8 and covalent bonding. Okay. All right. Have a good weekend, you guys, and I will see you on Monday morning.